you to everybody for joining us today. As
prevention is better than cure. Removing the source of pathogens so you don't need to try to treat them through chemical treatments, from Mike Domain of Dryden Aqua, and this is what Mike looks like. Mike Domain has worked in the aquarium industry for over 25 years. He started as an aquarist looking after penguins and a large live kelp forest exhibit, moved on to the animal collections team, and then went on to work on life support systems and water quality. Mike has experience in all aspects of aquarium life, including animal husbandry, exhibit design, quarantine, water quality, life support systems, operation design and management. He's been involved in the construction of 2 new aquariums, the Ushaka Marine World in Durban, South Africa, and the Dubai Mall Aquarium in Dubai, UAE, a new large open ocean display, and the renovation of 2 old large displays, sharks and kelp, at the 2 Oceans Aquarium, South Africa. Mike now focuses on developing or helping multiple facilities with their system requirements as head of the zoo and aquarium and aquaculture division at Dryden Aqua, a vendor at many animal conferences. And I've met Mike many times. I have to say thank you so much, Mike, for getting up early, because I know it's very, very early in Switzerland where you are. Can you hear me, Mike?
Yep, I can hear you. Can you hear me okay?
I can. That's fantastic. So I'm going to hand the screen over to you. You'll get a...
Yeah. Thanks a lot, Rob. I really appreciate the opportunity to present to everybody, and thank you to everybody for joining us today. As Rob was saying, I've been in the aquarium industry for many years. Now, let's see, there we go. Being in the aquarium industry for many years, I studied as an oceanographer, and then joined 2 Oceans Aquarium in South Africa in 1998, after volunteering with them in 94 when they built the aquarium. So it's been a long road in the aquarium industry, and I've really enjoyed every single day that I've been in that industry. So what are we talking about today? Really, most of my aquarium life has been spent in the life support side, and having experience, hands-on experience with animals and exhibits and all of that has really helped me to define my focus points in the life support side. And I think that's a vital part of why I see things slightly differently when I'm looking at a life support system, is because I understand all the water quality impacts in the background, and also all the impacts on the animals. Because at the end of the day, that's what we're there for, right? Is to make sure that the animals are as healthy as possible. So LSS really is, there are so many different kinds of LSS installations that are out there, and every designer would have a slightly different way of putting all of these components together. But at the end of the day, it's a combination of components to make sure that the animals within your care are being well looked after, and that the water that they live in and need on a daily basis is running at optimal levels. And particularly for many situations, the water needs to be as close to where those animals originated from as possible. So really it's the maintaining the balance in the water quality, and that comes from using these different components to make sure that you are treating the water to, first of all, remove what needs to be removed, but then also at the end of the day, maintaining the other chemistry balance that's required in the water. So it's not only a physical aspect, but it's also a chemical aspect. Before I move over to the next slide, I just want to reiterate again that this is just one possible layout of a system, and there are many, many more out there, many more options and opportunities to design an aquarium or a system. This really is a fish one, which generally will house the Elasmobranch as well, and it's built out of many different components, as can be seen on the screen. First of all, most or all exhibits would have a makeup water, whether that's a made water using salt mixtures to create the salt water that you house in your exhibits, like many inland aquariums do around the world these days. Then what's vitally important, and in my opinion underestimated in the design of aquariums, is the water movement, not only the turnover, and sorry, the turnover means the water going through the life support systems and all of the components back to the exhibit, but also the internal exhibit water movement. That is vitally important, because if your water movement within the exhibit is suboptimal, you will find that you'll have many dead zones in your aquarium where organics will go and settle in those dead zones, creating a lot of water quality problems. So one of the first things I have a look at when I visit an aquarium is what kind of water movement do they have in the exhibit? Have they got any corners where there's organic load settling and not being removed? Are the particles moving towards the intake system for the life support systems or the overflows of the exhibit? And those are generally the aspects I look at from water movement in the exhibit perspective. Then the next step would be the removal of particles, and please bear with me. I know that this is all very obvious in many steps, but I am leading to a point further down the line, so bear with me. So removal of the particles in the water is vitally important, and more often than not, that is done by media filters in most aquarium systems. I will get to a little bit more detail on that later on. Then the third step in the system would be your TDS or DOC, dissolved organic carbons or fines removal, and this is more often than not done in the modern aquariums in foam fractionators, protein skimmers. They often referred to as protein skimmers in many parts of the world, or even carbon filtration. One of the most important steps in your system is biological filtration, and this is where you are trying to deal with the most toxic of the chemicals that are created in your systems, the ammonias, and shifting those towards the nitrification phase, which is the least toxic. And that is then generally flushed out by the makeup water, or in some situations that the system would include a denitrification step. Okay. Of course, there are many auxiliaries to these systems, including temperature control, pH and alkalinity, ozone. There's a whole range of additional add-ons to these systems to maintain them, depending on what part of the world you're on and what water criteria you need to adhere to, depending on the animals that you have in those exhibits. So if we take a step backwards and talk about what we are trying to achieve in these exhibits, right? Like I was saying earlier on with the biological treatment, that is one of the most important aspects of your system, and the one that's going to create you the most problems if not looked after correctly. With regards to Elasmobranchs, which are very prone to parasitic infestations and pathogen infestations. This often is a source of those pathogens. So let's make sure that we deal with your organics cycle correctly. We all know the general organic cycle, where your food is being created into ammonia, and the ammonia then needs to go through the nitrification cycle, and then is either released, the nitrates are released by flushing, or in some situations, facilities have denitrification systems. We won't go into the details of those because they can be quite complex discussion points and presentations on their own. The main point of today's topic is what are we going to do with these organics in the system to make sure we do not overload our biological filtration. So really, the bottom line is the more of the organics we can remove out of the system, the focal point should be organics removal, the more effective the whole system becomes. And now remember that these are of great scenario that you're looking for. And if we can make components as efficient as possible, your removal becomes as effective as possible, and therefore your overall biological cycle becomes as effective as possible. So if you remove the organic and denitrification or flushing is reduced dramatically. All right. So how do we do that? I mean, again, there are so many different ways of doing this, but there are a couple of general ways, and that is large particle removal. These are particles often referred to as greater than 20 microns in particle size. They can be drum filters. I see the rise of drum filters in the aquarium field. That is a presentation on its own. There's screen filters, wedge wire filters, there's cartridge or bag filters, and then the standard, which is we see throughout most of our aquariums, is the media filters. The next step down is the fine particles removal, which is particles greater than 1 micron, sort of between 1 microns and 10 to 20 microns. This again can be cartridge filters in low flow requirements or small systems. Often we see these being used for the water going to your culturing vessels, or otherwise media filtrations with with carbon or some of the glass medias that can achieve 1 microns media filtration. And then one of the biggest components used for this is foam fractionation or the protein skimmers. And we'll go into a little bit more detail about that. If you are trying to achieve sub 1 micron filtration, that really requires that you have a coagulation / flocculation point. And in aquariums, that is generally ozone that is being used for that. Again, that is another whole presentation on its own. We'll discuss it slightly, but one day we should do a full presentation on that too. What my experience and what I've seen around the world, seen over 70 aquariums around the world, I strongly believe that our design philosophy has moved towards complexity and also how to solve problems. Now, when you say that, it sounds like the right way to go. But if we're trying to solve a problem, we've created a problem. So surely if we take a step backwards, if we look at how we created that problem and prevent that, then we are preventing the problem, and therefore all the repercussions down the line that that problem causes as being reduced or even removed. Just let that sink in a little bit. And that's where the comment prevention is better than cure come from. So back to the organic cycle. What have we forgotten? Because the organic cycle is not that easy, right? We remove the organics, we get rid of the ammonification, and therefore the ongoing nitrification cycle, we reduce that dramatically. But what have we forgotten? We've forgotten that fish are continuously excreting ammonia out of their gills too. So there will always be ammonia component to these systems that we need to deal with. What's the other thing that we've forgotten? The other thing that we've forgotten is that every surface within your aquarium, whether it is the gravel on the base of the aquarium, the walls, the rockwork, the artificial theming, even down to the piping that moves your water to and from the exhibit, will have a component of bacterial colonization and therefore biofouling. And within that biofouling, we are removing organics and also producing ammonia. So those are the points that should be the main focus, is how, if we remove all of the organic load that we are introducing into the system by feeding the animals and the excrement that they produce, all that we should have to deal with is the ammonia being excreted from the fish, and that coming from the biofouling on the surfaces of the exhibit and the piping. Right. So in doing that, we dramatically reduce the amount of a biofiltration surface areas that we need to deal with ammonia, making the system far more efficient and effective. One of the main reasons why this has become more and more of a focal point of mine is that in working in the aquaculture scenario, this is a key driver in aquaculture. Because of the high loading densities, they generally have incredibly large biological filtration media. And in that biological filtration media, in the way that they set up their systems, is it allows for a lot of particles, organic particles, to be filtered out by the biological media. So what does that mean? First of all, we're expecting, here's the fish in the feed, we are first producing ammonia before we are going through the nitrification cycle. So that's the problem, right? Why create something that we are trying to deal with down the line in one of our system components? The more we can remove those particulates, the less ammonia we are creating, and the better our systems will operate overall. If we have a look at if you do your own search on the internet and look at biological filtration, it's a nitrification step, right? It needs oxygen. It's an aerobic process to facilitate the fast breakdown of particulates. And as the process shows you, without oxygen, without enough oxygen in your system, you cannot do the nitrification step. Not only that, is during this nitrification step, your pH tends to get depressed because you're releasing hydroxyl ions, and your alkalinity is consumed because you are creating bacterial cell biomass, and that biomass needs alkalinity to create its cell walls and for the cell functioning. All right. So if you don't have enough oxygen, and this is what we often find in aquaculture systems and some aquarium systems, your pH will dramatically be depressed. Your DO, or dissolved oxygen levels, drops even further, and to some extent can be zero on the outlet of your biological filtration. Also, this component, the fish feed and those particles moving onto your biological filtration, shifts the biome, the bacterial biome, from an aerobic autotrophic process can shift it into an anaerobic heterotrophic process, or if you've got enough flow through it and enough oxygen moving to it, it won't be anaerobic, but it will be an aerobic heterotrophic process. Now, why is that important? Because your system is therefore being dominated by the bacteria that are needed to break down particles, rather than the autotrophic bacteria needed for the nitrification cycle. So just let that sink in a little bit. we are often creating the problems that we're trying to deal with. If we have a look at how that happens, you'll look at your biomedia, and yes, biofiltration can come in many different forms. I'm just going through one form. Well, not really one form. I'll briefly mention the other form, but this is moving bed biological reactors that use these little bio balls or bio discs or whatever you want to call them. In many aquariums, we have the trickling towers, and from my perspective, the trickling towers are far more effective than moving bed bioreactors. But if we look, this just showed really nice photos of a surface becoming overloaded with bacteria and biofilms. As you can see in the middle picture, the top one is a clean bioball. The next one is bacterial colonization throughout that cell. And then the third one is when you're overloading your biofilters with too much organics, and your heterotrophs grow to such a point that they start to block the full surface area within within the biomedia. And that is important because as your bacterial cell mass becomes thicker and thicker, the more you start reducing your pH, your oxygen, and also you're creating anaerobic zones within your media that you would think is a oxygen-rich environment. So even though you measure your oxygen on the inlet and outlet, and you go, well, we're still in acceptable levels. Oxygen coming out of the system is fine. But what you don't realize is that within that thick biofilm in these discs, or even on the surface of your trickling towers, that is where you have anaerobic zones and low pH and heterotrophic bacteria. The perfect place for viruses and parasites to breed and grow and spread throughout your system. There are many aquariums around the world that use, well, hold on, let me rephrase that. There are aquariums, not generally around the world, in certain parts of the world that strongly believe in sand filters being used as not only particle captures, but also as biological filtration. Again, if you put too much particles into a vessel, you are creating a heterotrophic dominant bacterial biome instead of an autotrophic dominant bacterial biome. If your flows are not optimum, your pH will be reduced as you go down through your media. Your oxygen will be reduced as you go down through your media. At the point of where your, say, clean water is coming out of your filter, you have low pH, low dissolved oxygen, which is not ideal depending on how your system is set up. Many systems out of their sand filters goes straight back to exhibit. If they go to a biological tower, then that's okay, except that you are putting oxygen poor water, low pH water in the top of your biological tower, making it less effective. Okay. Your ORP is reduced because your oxygen levels are dropping. Your requirement for pH increases substantially, depending on your recirculation rates. And like I was saying, your anaerobic zones, you're increasing the percentage of your overall anaerobic zones throughout your system. So you really don't want to be able to facilitate bacterial growth in the filters, which is prone to low oxygen environments. Okay. There we go. Okay, ozone. And we all, well, I hope that we all know the risks of ozone, particularly in seawater systems. But ozone, in my view, and what I have seen often around the world, is incorrectly used as a very high level sort of sterilization dose in a contact chamber slash fractionator. ozone is really good at breaking down particulates, but is that what we want to do? So that's the question we need to keep asking ourselves when we look at our system components. What are we trying to achieve with this component? Okay, so if we look at ozone in a contact chamber or protein skimmer, if you are dosing high dosage rates, then you are breaking down your organic particles into dissolved organic carbon before you're then trying to remove that later on down the stage. So as I said earlier on, ozone is an incredibly good coagulant flocculant that is used in many applications around the world, from swimming pools to drinking water to everything. But the experience I have with the use of ozone in aquariums is that we are too reliant on it as protecting us from viruses and pathogens and bacteria, parasites. And in a single contact zone within the, sorry, I'm losing track of my thinking here. It's 4 o'clock in the morning. So within those contact chambers, whether they the cone-shaped contact chambers or the protein skimmers, that's where you have the dosage rates that are sufficient to kill these bacteria and parasites, but you definitely don't want those levels transferring down onto ongoing systems, or you will be creating problems on your fish and your Elasmobranch gills. We do know that Elasmobranchs are highly sensitive to changes in water quality, and they are generally the first ones that will start to show signs of those changes, whether it is due to high TRO levels or to residual other residual oxidants in the water, or just instability in your water quality. It's always going to be your Elasmobranchs that are going to break out in a parasite infestation first. And more often than not, that's going to be on the gills, right? Which is your thinnest membranes in the animals, and where you start to get the gill parasites or gill flukes being generated, because those are now trying to survive themselves in this high TRO levels, so they breed like crazy. I have had my fair share of problems with these gill flukes in both sharks and also rays. Sorry, that was a great presentation earlier on, Chris. I really enjoyed that. And yeah, so we want to avoid those problems. We want to avoid dramatic changes in water quality and water chemistry, because Elasmobranchs are the first to react to the signs of these water changes. So if you dose ozone effectively, when I mean effectively, that means as low as possible to generate a coagulation flocculation process, rather than trying to aim for a sterilization process. And we, yeah, so I've had some of my fair share running at very high ORPs, even to the point at 700 millivolts, leaving the filtration systems, going back to the exhibit, and then also running at standard ORPs of 450 millivolts. And that's really where you should be aiming, right, is your 450 millivolts going back to your exhibit. That is running at a flocculation dose and a stable dosage that's going to help to remove the particles rather than break down those particles. The next slide is a little bit intense in terms of writing, but when we look at these components, what do we as LSS professionals need to check? And as an aquarist running a system, these are a list of items that I would highly recommend that you check straight away. Have a look at your systems, do an efficiency autopsy on your systems, so that you can see that your systems are performing as they should be performing, and each of those components are working correctly as it needs to. One of the biggest problems that we find in media filters is that the operational pressures, or the pressure differential between the inlet and outlet, is running very high. So if you're running at greater than 9 psi pressure differential, so that's again the difference between the inlet pressure and the outlet pressure. Our experience in filtration around the world, and a lot of it in aquaculture, is that if you run at those higher pressures, you are actually breaking your organics down into finer and finer particles, because the organics are so soft that they just get sheared through your media bed. So that's why we have our recommendation of backwashing at a maximum of 9 psi pressure differential over your filter. Okay, vitally important. We see this a lot in aquaculture systems where they are creating fines out of their larger organics. All right. These fines, as they become finer and finer, obviously are not being removed out of the system, and therefore accumulate throughout the whole system, just purely in the turnover of your water. I've seen in a swimming pool environment where the water became white. Yes, white, like milk, because they were running their systems so fast. They had a very high bather load, and they were never removing any of their particles. They were just breaking them into smaller and smaller pieces. Step 2, filtration velocity. One of those items that is quite often misunderstood, because when you go out and buy a filter, and this is often, you find this in smaller aquarium systems, you'll go and have a look at a filter. Your filter will say it can operate at 50 meters per hour, cubic meters per hour per square foot, which is round about 26 gallons per minute per square foot, I think it is. Sorry, I didn't write that in there. And you think, oh, the filter manufacturer says I can operate at this velocity, so we must be able to operate at this velocity, because that means I need less filters. That saves me costs. I need less pumps. That saves me costs. But actually, at the end of the day, filtration velocity is the next impact on creating fines, because we can very clearly show that at velocities over 25 meters per hour in aquariums, you will be shearing your particles into smaller and smaller pieces rather than effectively removing them. Media has very aspect on it. You're going into the filter and out of the filter. And you might, this can also be NTU as well. Well, preferably TSS, which is going to give you a better understanding of what's actually in the water. NTU is just an indication of what's happening in the water. So your TSS level, you would think, coming in and going out should be the same if your filter is channeling. But quite often we find that because the biological activity within sand beds, your TSS on the outlet of your filter can actually be higher than your inlet TSS. Just want to let that sink in a little bit. So this will increase the load on your biofilters and on your fractionators, because you're taking the particle sizes from 20 microns and you are breaking them down into finer particles, putting more load on your fractionators. And if those particles are being caught up in your biofilter, you're shifting that biological regime into the heterotrophic regime. So a very important point with media filters is what you capture in the media filters has to be released at the backwash stage. And more often than not, this is the step that we find is failing in globally, whether it's in swimming pools or drinking water or desalination, is that the backwash velocities are not great enough to expand the media bed, creating the space between the medias to allow that dirt to come out of the filter. All right. Some medias can backwash at 35 meters per hour or 15 gallons per minute per square foot to get good bed expansion of 20%. That's sort of a baseline. If you look at the German DIN standards, they say 15% should be your target. Our experience is that it actually needs to be 20% to ensure good removal of dirt. That does not only come because you are expanding the bed to 20%, but the shearing forces at that 20% bed expansion helps to break the dirt particles off your media. Okay. So if you're capturing media and you're not getting rid of it during your backwash process, you have not only are you holding a residual load and your media filter will collapse over time, but also you're leaving a lot of dirt within the filter, which is then contributing to your ammonia problem and increasing the load on your biofilter down the line. We talk as Dryden Aqua, we talk a lot about backwash regimes, and just to show you that this is not us, Dryden Aqua, saying this. This is a recommendation by Evers, which is a German manufacturer of anthracites, carbons, sand, and this is their recommendation for backwashing. So as you can see, with the smallest grade of sand size, so that's your first question to ask, is what grain size do I have in my filter? And am I backwashing correctly for that specific grain size? Okay, so here you can see 0.4 to 0.8, 35 to 40 meters per hour, or 14 to 16 gallons per minute. If your grain size is 0.71 to 1.25, and I do see this a lot in aquariums, then you need 50 to 60 meters per hour, or 20 to 25 gallons per minute per square foot. If you go bigger than that, which I don't often see, but sometimes I see this in smaller exhibits, and also land animal exhibits such as hippos or elephants or things like that, I often see these big grain sizes in these filters, and they are still backwashing at the 14 gallons per minute, where they should be up at the 33 to 37 gallons per minute, or 80 to 95 meters per hour. All right. When we look at fractionators, ask yourself, what are you trying to achieve with your fractionators? Your fractionator is there really to try and help you deal with the very fine particles in your system, and even to the point where you can remove TDS. So total dissolved solids, or even DOC, dissolved organic carbon. You can flocculate those out of the water, keeping your water stable for much longer without needing replacement. And really that's what your protein skimmer should be doing, gearing towards those fines. It should not be trying to capture the larger particles between 20 and say 5 microns that break through normal sand filters. It's not focusing on that, right? It should be focusing on the less than 5 micron particles, and preferably less than 1 micron particle sizes. We often find that if your protein skimmer is not working optimally, and we really go with the manufacturer's recommendation here in terms of that specific protein skimmer's turnover requirements or residence time requirements, but generally that's around about 2 minutes. If your residence is faster than that, you will be producing organics and releasing that into your downstream system. I've seen this in many situations. So do yourself a favor, have a look at what your inlet TSS is and what your outlet TSS is. You might be surprised to find that your protein skimmer is very good at removing your TDS or your dissolved organic carbon into particulate form, but it's not operating well to remove that out of the water and lifting that to the surface and out the cone at the top. This is also often a result is if you're not monitoring your protein skimmer and you're not managing it correctly. So during the periods, I would say 2 hours after feed events where your protein skimmers generally work very well, that period in between, you are still creating particles through the coagulation flocculation process, but those particles are not being removed out of the filter because the amount of dirt is so much smaller that it doesn't form enough of a foam to build up out the top. Secondly, that foam tends to cling to the cone at the top of the outlet, and that creates that effect creates that the foam implodes on itself all the time. It falls back on itself. So you don't remove the particles if your cones are not clean enough. And those particles get to the point where they grow that the air is not enough to keep them at the surface, and then they drop down into the water volume and go and travel out of your protein skimmer. So monitor that process. Yes, I understand, and I've operated many protein skimmers in different facilities. They are not the easiest. Actually, let's just be clear. They are a nightmare to try and make them operate continuously because they are operating under different water quality throughout the day. And unless you have an automated system that is monitoring the water level and the ejection on the foam on the top, it is very difficult. If it's a manual system, yeah, it's pretty much impossible because we don't have the time to stand at these protein skimmers and adjust them all day long. We need to be practical. And then again, just ozone should be used in these systems as a coagulation flocculation dose. Great, the video is actually working. It wouldn't work for me earlier on. So the biofilters, what to check in the biofilters. This is what we call a MBBR, so a moving bed bioreactor, which is often used in aquaculture facilities. Not so much in aquariums, maybe on smaller exhibits. You might see these being used. For me, still, the premium biological filtration method is trickling filters. And I know there are some facilities that have done some research on this in the past. I think you can find some papers in the Drum and Croker, or you can contact Monterey Bay about their testing. I'm trying to encourage them to publish their old findings again. But yes, your biofilters are, what can you check there? You can check your inlet and outlet TSS. So are you creating organics in your biofilter? I can tell you in aquaculture, they often create a lot of organics in their biofilter, which they are releasing into their system, increasing their bioload, or as a massive amount of sludge at the bottom of those filters, which they then need to pump out because it impacts on their oxygen dosing and their water quality, pH, all of that. You can check what your ammonia is going into those filters and out of. Is your system working correctly? That will then require nitrites and nitrate testing to see how efficient your system is working, and you can adjust your flow rates according to that. You can check your dissolved oxygen in and out, because if your oxygen is very low on the outlet, either you are not aerating your trickling filter well, or your MBBRs, or your flow rate through the filter can be a little bit on the low side. Your pH, alkalinity, and hardness are all impacted on that by your biofilter. And that's one of the things, the more organics you have in your biofilter, the more you're going to have an impact on your pH, your alkalinity, and hardness. And that is where we talk about reducing the amount of chemicals being needed in your system, is if your biofilter is working efficiently. Okay. Point 2 really just steps back to using sand filters as biofilters. Yeah, let me not go down that route, but it's a challenging way to do biological filtration, and one of the main reasons why that is because you don't have direct control of what is happening within your sand media. Whereas a biological filter or trickling tie, MBBR, you have a lot more control as to what you're putting in, how you're operating it, than you do in a biofilter, in a sand filter being used as biofilters. It is far more effective to have a small biofilter that you are relying on and operating correctly than using a sand filter as a biological filter. So if you have a look at the overall results of all of these, you'll be able to assess how well your biofilter is working. Okay. So at the end of the day, we look at it in this way. Is your system fighting, are your system components fighting against each other, or are they working well together in collaboration? And when we're talking about working well together, I mean that each component is working as it's designed to work. Your media filters are removing particles, possibly down to 1 micron, depending on the media that you have in there. Your protein skimmers are removing DOC, TDS, particles less than 1 micron in size. And your biofilters are operating to function effectively and efficiently as the nitrification step, not as a particulates filter first off and then the nitrification step. Of course, being an Elasmobranch system, we can not only look at what your LSS components are doing, we also need to look at what's happening in your system, because many of these animals, as Chris was saying, like to sit on the floor during their rest periods. And if you are not cleaning your exhibit very well, and that includes vacuuming or siphoning your media and your surfaces within your exhibit itself, your risk of pathogens is far greater, because if you have your life support system working effectively, it won't be contributing dramatically to the pathogen load, but your gravel in your system could be a very big source of your pathogens, right? So make sure you are cleaning your exhibit, just like your life support system is cleaning your water that's moving through the system. You also need to clean your exhibit. If you have good exhibit circulation that avoids particulate settling down onto the gravels, your need for diver cleaning is dramatically reduced, because then your filtration system will deal with those organics. I said reduced, not removed. Please, I hear some aquariums out there that have not vacuumed or siphoned their gravel for years, and that's just a time bomb waiting to happen. Okay. It's a collaboration of systems again. It's a overall looking at the overall performance of every aspect, and one of those aspects is cleaning your exhibit. So as a quick summary, if you do your organics removal very well, you will reduce your ammonia creation, which reduces your nitrates at the end of the day. You reduce the amount of ozone you need to use in your system dramatically, because then you really are just focusing on the coagulation flocculation, not trying to break down particles by ozone. Your pH is far more stable so you don't need to add pH buffering chemicals. Your parasite loads comes down, because if you get your media filtration backwashing correct, and you don't have biofouling in your media filters, then you, when you backwash, any parasites that you have caught out in the media filters, you will be backwashing those out. Your clarity of the system will increase, which doesn't really matter that much for the animals, except that you have visitors that come to see your aquarium, so they want to see things as clean as possible. It also has a psychological impact on whether your guests think you're looking after your animals correctly or not. It also gives you the opportunity that your stocking density can be higher. And I see aquariums running with very low stocking densities, and that's purely because their designed LSS systems are not working optimally because of a lack of understanding of how to operate each component correctly. All of this then reduces your costs and reduces your maintenance while increasing your fish health. Of course, when you are designing a new system or having troubles with a system that you have had a look, you've done your root cause analysis or problem solving of each component, and you are still battling with a certain issue, please always consult a reputable LSS engineering firm to help when you get stuck. This is vitally important. Because as we know, fish, animals, only have disease and parasite problems when they become stressed. And that stress factor is often can be caused by many, many different reasons in an aquarium, but mostly because your biology is not being looked after correctly. And that changes your water quality aspects. It increases your breeding zones for viruses and parasites, and you are trying to dose too much with ozone. So that I can speak to directly, because at one of my facilities, our shark tank would always have an outbreak of gill flukes every time our ozone generators went down. So what does that mean? Does that mean that the system had to use ozone? No, that means that we were running, and this was one of the facilities where I was running a very high ozone ORP levels for other reasons that we don't need to go into now. But yes, when an animal gets used to a certain operating environment, if you change that operating environment very quickly in terms of the water quality that it's experiencing, they live in this water all the time, and they detect that change very quickly. And like I was saying, especially Elasmobranchs, and just that change creates the stress factor, which then pushes them over, creates a situation where the parasites have to survive because they think that something's changing, and you have the outbreak. Stability is the key. And stability in water quality can only be achieved if all of your different components are working together. One of the main points that I live by and encourage everybody else to live by is that no question is a stupid question. It might be stupid for you because you've been in the environment for a very long time and you consider that as something that people should know. But remember that throughout our learning cycles, starting in aquariums, we can't know everything. Even today, as I sit here, there's by no means do I consider myself an absolute professional in anything. There is always a different thinking process that could lead to a different outcome or a different solution. But what we do like to strive on in Dryden Aqua is prevention rather than cure. And that's a key point to reducing all of the problems in these systems. So at the end of the day, it's simple, isn't it? Thanks, guys. I appreciate you spending the time with me today. I spoke a little bit faster than I think I was going to speak, but I've ended the talk, and I'm happy to take questions. Just a little bit of advertising. If you want to see more details, we do have a Aquaria and Zoo webinar series on our Dryden Aqua YouTube channel. You're welcome to go and have a look at that. There's a 6-part segment there that talks to different aspects, whether it's fish, whether it's marine mammals, filtration, water turnovers, just the background basics of a life support system and the implications of that on specific applications.
Many thanks, Mike.
Thanks again.
Just leave that slide up. First of all, congratulations. I know what it's like to get up in the middle of the night and give a presentation, and I thank you very, very much again for that. A couple of things I just want to reiterate or stress is the importance of oxygen for your biofilter. And the figure that I have, we always think that it's the animals that consume the oxygen. Biofilter is a big part. For every 1 kilo of ammonia, you utilise 4 kilos of oxygen in that ammonia to nitrate process. And so biofilters are a huge consumer of oxygen in systems, and that's something you really need to consider. And the other thing I wanted to stress again was the substrate cleaning. The number of times I've seen a cryptocarian, a white spot outbreak, or as you said, an increase in your fluke, your monogenians, because the substrate wasn't cleaned regularly and the staff were away sick, or we had people on holidays, so that got pushed to the side. I can't reiterate the importance of substrate cleaning. And if it's a big ocean tank, have a map. It's broken out into the different sections that are done on a weekly basis, or so you get around the whole ocean tank every week or two. That's absolutely critical. Ellen has asked a question. Our ozone equipment is set to automatically shut down if the exhibit ORP level reaches 365 millivolts for animal safety. Is the 450 millivolt you mentioned the high end of ozone tolerate for Elasmobranch or an average?
So it would be a high end, definitely on the high end side. Generally your ozone operations are operating between the 350 and 450 range, depending on your exhibit, the number of animals in the exhibit and the type of animals in the exhibit. However, having said that, as I was talking to the experience of the sharks that broke out in parasite infections when the ozone failed, and yes, that was not a on-off during normal operations, it was when the ozone generator failed. Animals like to have a continuous balanced environment. So when you're operating your ozone, again, if you operate at a flocculation dose, you will generally be operating at a much lower level for a much longer time. Okay. Don't try and get rid of all of your COD and TDS in the shortest possible space of time after your feed, because that's when you're using the higher ozone dosage, not talking to ORP, and then that also means that you increase the risks of potential problems with gill, filaments, eyes, whatever it is. Rather keep your ozone going for longer periods in your protein skimmers.
Yeah, and look, the only other thing I would chime in with is I get worried when everyone just relies on ORP sensors, because they need a lot of maintenance and have been known to fail. And so I think anyone that's using, and please agree or disagree, Mike, but anyone for me who's putting ozone into their system in their foam fractionators needs to do a TRO test on a daily basis just to make sure that they're not getting a build-up of those oxidants.
Highly agree, Rob. Highly agree. We, on my facility in Durban, Ushaka Marine World, we actually had three ORP sensors on the system. 2 on the outlet going to exhibit, 1 a gold and 1 a platinum probes, so that we were covering all possible events. And even with that, we had 1 failure that resulted in a full exhibit loss at one stage. So these things, ORP sensors need to be maintained correctly continuously. However, if you are working on a low ozone dose, you have a much higher chance of picking up that increase in TRO levels on a daily basis than you would if you're operating at a high at a high ORP level or higher ozone dose that can result in immediate failure and deaths to the animals. So again, low levels, dosing is better.
Yeah, and I've seen a complete dip like that. It's not good. I think I'm going to leave the last question / comment to Ellen because I think it's really appropriate. So Ellen says that TRO tests help me sleep at night. And I think with that, Mike, I'm going to say goodbye because I suspect you might want to try and go back to sleep for a couple of hours before you start